We're going to finish up our design example with conductor sizing and grounding. Let's go ahead and get started. We'll be following the conductor sizing steps that we laid out in a different lesson. First off, we need to determine our maximum circuit current. For the DC to DC converter circuits, remember there's two of them, we follow the manufacturer's requirement. These are going to be electronically controlled by the inverter and optimizer. Per the manufacturer, they are limited to an output of 15 amps. So that's our maximum circuit current. For the inverter, again, per the manufacturer, it's limited to no more than 32 amps. We already have seen that number earlier. Then we can calculate our minimum overcurrent protection device size. For the DC to DC converter source circuit, no fuse is required for one or two circuits on this inverter. Just like with regular PV source circuits, connected one or two in parallel, no source of overcurrent. As long as the inverter cannot backfeed, there's no need for overcurrent protection. You can see the wiring cabinet here on the inverter. There's the two strings coming in. They're paralleled, and then they go out to this disconnect and up to the inverter. So no fusing required in this case. On the AC side, the inverter output circuit, 32 amps times 1.25. That's our required multiplier for the minimum OCPD size, results in a 40 amp overcurrent protection device on the output, and that is a standard size. And again, as we said earlier, we're always going to use the minimum calculated size, not the manufacturer's maximum, unless there's a really good reason. One thing I did want to point out about this particular inverter, you can't exactly see it, but this little mounting bracket here tips down so that you can access the wiring. And on the front of that is a revenue grade meter, which is an option for this inverter. You can see a CT here for the output monitoring. And this is an optional revenue grade meter that then be connected to the data acquisition system. In some cases, you may need that. In some cases, the monitoring may be done externally or by other means. All depends on what you're looking for. So next up, step 3, required DC conductor ampacity. We'll look at the DC to DC converter circuits. We have two of them, 15 amps maximum circuit current each. And we size these based on 690.8A1C. We'll be using THWN-2 copper conductors. They have a 90° C rated insulation, and these two circuits are going to be together in a single conduit. They'll be run together, maybe to a box on the roof, and then transition into a single conduit running down from there. The ambient high temperature is 37 degrees Celsius. We looked at the ASHRAE data earlier. Going to table 31015B1, we have a temperature correction factor of 0.91. And we have these two circuits, two current carrying conductors each, 4 current carrying conductors in the single conduit, so we need to apply the 31015C1 adjustment factor of 0.8. Now, one thing you'll notice that's not on here is our rooftop adder of 33 degrees Celsius, because we are being smart and we're keeping our conduit at least 7/8 of an inch above that roof surface. That way we only have to base wire sizing on the ambient high, not that rooftop adder. So if we apply our factors, and we know that the conditions of use, because that together they are less than 0.8, in fact, one of them is 0.8, they're going to drive conductor sizing. Our other option for conductor sizing is what? Maximum circuit current times 1.25. Here we're looking at maximum circuit current adjusted for conditions of use. Whichever is the larger is our required ampacity, and we know that the conditions of use, because of the two factors we're using, are going to be the larger. Take the maximum circuit current, 15 amps, divided by 0.91 for our temperature correction factor, divided by 0.8 for the 4 current carrying conductors and conduit. We need a conductor with a rated ampacity of 20.6 amps. We go to table 31016 in the NEC, and we can see that a 14 AWG THWN2 copper conductor with 90° C insulation is rated at 25 amps, so that would be sufficient based on these calculations. Now let's go through step 3 for the inverter output circuit. We've got, again, THWN-2 copper conductors, 90° C rated insulation. We'll be using a single conduit for this one inverter, obviously. Again, we've got that same ambient high temperature, 37 degrees Celsius. Temperature correction factor is the same, 0.91. In this case, we've got 3 current carrying conductors, so there is no need for an adjustment factor. It's once we hit 4 or more that we start to apply adjustment factors. So in this case, the temperature correction factor is greater than 0.8. There are no other correction factors. That means conditions of use are less extreme than Imax times 1.25. Thus, IMAX times 1.25 is going to give us our required ampacity. And you know what? It's the same as our minimum OCPD size. 32 amps IMAX times 1.25, 40 amps. Going to table 31016, looking in the 90 degree C copper column, we see that a 10 AWG THW-2 conductor is rated for 40 amps, exactly what we need in this case. Now we've got to make sure the overcurrent protection device actually protects the conductors. It doesn't always work out because of Roundup and other requirements that are in there. Now there is none for the no OCPD for the DC to DC converter circuits. Nothing to check here. What about that inverter output? 40 amps overcurrent protection device. We've selected a 10 AWG copper conductor that's rated for 40 amps, but we know that if we look into 40.4D, small conductors, 14, 12, and 10 have maximum overcurrent protection device sizes that they can be connected to, and for a 10, the biggest OCPD you can use is 30 amps. So it doesn't work. We need a 40 amp breaker, that's the minimum size. Even though 10 has enough ampacity, cannot be protected under the National Electrical Code by anything bigger than a 30. That means we need to do what? We need to go to a bigger wire, upsize it to the next size, 8 AWG, copper THWN-2. That conductor, under the conditions of use, we take its 55 amp rating from table 31016 in the 90 degree C column, we apply that same 0.91 temperature correction factor, and we see that the conductor has a corrected ampacity under the conditions of use of 50.5 amps. It's protected by a 40 amp overcurrent protection device. We're good to go. We get the green check. How about terminal temperature limitations? We got to make sure our wire doesn't get hotter than the terminals it's connected to. The wire's got 90 degrees C insulation. A lot of times the terminals are 75 degrees C rated. We've got to make sure the conductor itself doesn't get warmer than that. That means that our step 3 value, the maximum current times 1.25, or the maximum current adjusted for conditions of use, whichever's bigger, that value's got to be less than or equal to the chosen conductor ampacity based on the column from table 31016 that matches the rating of the terminal. Right? So if our terminals are rated for 75 degrees C, we're going to look at the 75 degrees C column for that wire size and make sure that it has ampacity equal to or greater than the step 3 value. Okay, for the DC to DC converter, we had a corrected circuit current or adjusted circuit current of 20.6 amps. That was our 15 amps IMAX, our maximum current of the DC to DC converters, divided by 0.91 for the temperature correction, divided by 0.8 for the 4 current carrying conductors in conduit. That gave us 20.6, our step 3 value. Well, if we look at a 14 AWG conductor in the 75 degree C column of table 31016, we see that it is only rated for 20 amps. It's not big enough. It doesn't have enough ampacity. We need to go to the next larger wire, 12 AWG, and if you look at its rated ampacity, it's going to be sufficient for that 20.6 amps. What about the inverter? We had a step 3 value of 40 amps, and if we look at the 75 degree C rating of the number 8 conductor, that is going to be 50 amps, so it exceeds the step 3 value. We're good to go with the 8 AWG wire for our AC circuit. Finally, we need to look at voltage drop. The DC to DC converters, we are using 12 AWG conductors. We go to Chapter 9, Table 8, and get a resistance per 1,000 feet of 1.98 ohms. We have a 50-foot one-way distance that's just measured out for this particular system. And we know that each of these circuits is 15 amps. They're run separate, so we're just going to calculate it for one. And they're operating at a nominal DC input to the inverter of 400 volts. We drop our numbers into our calculations to solve for percent voltage drop. 0.2 is our constant, 50 feet is our one-way distance, 15 amps is our current, 1.98 is our conductor resistance, divide by the voltage of 400, and we come up with a voltage drop of less than 1%, 0.74. That's great. We're looking good there. Our wire is big enough for the ampacity requirements. It's also big enough to give us suitable voltage drop. 12 AWG for the DC to DC converter circuits, it is. Same calculation on the AC side for our 7.6 kW inverter. We're using an 8 AWG copper conductor. Chapter 9, Table 9 for AC. Resistance is 0.78. We've got a 10-foot distance. It's right next to that service panel. And it is 32 amps at 240 volts. To solve for the percent voltage drop, again, 0.2 is our constant, times the one-way distance, times 32 amps, times the conductor resistance, divide all that by 240 volts, and we get a really nice low 0.21% voltage drop. Nothing to worry about here. Inverter's not going to have any problems with that. We're not going to have any significant power loss. So both of these conductors look good in terms of meeting ampacity requirements and voltage drop requirements for their respective circuits. Finally, let's talk about grounding for our system a little bit here. The modules, in terms of bonding them, we're going to be using racking that's listed to UL 2703. So there's no additional bonding required. The clips are going to connect the module frame to the rail. We're going to connect the rail to an equipment grounding conductor. Now we have to make sure that separate sections of the rack are bonded together. That might be the two rows, for instance. We're going to need a bonding jumper between those to make it all one piece of metal. But as long as our modules are listed to work with the rack, they're compatible. You need to verify that as a system designer. The module grounding is, I hate to say take care of itself, but as we mount the modules, they're going to become bonded, and then we just need to run that EGC down. So from the array to the inverter, we're going to be running a 12 AWG copper EGC that's based on table 250-122 and the assumed overcurrent protection device of 15 amps. So 15 amps in this case, maximum circuit current. A 12, I think, is good for 20 or more, so we're good to go there. You do want to keep in mind that where subject to physical damage, the EGC is going to have to be larger. So where it connects to the racking on the roof, for instance, your AHJ may say, oh, stuff on the roof is exposed to physical damage, so you run a number 6 until you get to the transition box where the output circuits from the converters are transitioning to conduit, and from there we drop down to that 12 AWG copper conductor. This is going to run and it's going to connect to the grounding electrode system, but it's going to do that through the inverter and then through the inverter output circuit equipment grounding conductor all the way back to the point of interconnection, right? We don't need a grounding electrode conductor. The EGC from the array connects to the inverter. The DC side of the inverter is bonded to the AC side of the inverter, and then that continues on to a ground bus bar, probably in our service panel. There, our AC EGC is terminated, as well as an existing grounding electrode conductor to the grounding electrode system. That's all we need in terms of connection to the earth for the PV system itself. Yeah, so the EGC from the inverter that's going to make that final connection back to the point of interconnection is going to be a 10 AWG copper conductor. Again, it's based on the 40 amp overcurrent protection device. We just look it up in table 250-122. It lands on the bus bar in that service panel. We've got a bunch of other grounding wires landing on that bus bar, and there's going to be a grounding electrode conductor running to a ground rod or a UFR ground or whatever the existing grounding electrode system is for that house. We didn't change anything about the existing service entrance conductor size. We don't need to change anything about the AC grounding electrode conductor or the AC system bonding. We know that we've got a transformerless, non-isolated system on the DC side. This is all we need in terms of grounding to make it code compliant. All right, well, I hope you enjoyed the presentation. I will talk to you again sometime soon. Thanks.